Hello and welcome to the 10th series of lectures in real analysis. So for the first part of this lecture, we will discuss integration through image measures. First, let us recall the definition of an image measure. For the domain, suppose I have a measure space, x sigma mu, and I have a mapping f from x into y, where y is some measurable space, and a tau or t here is the corresponding sigma algebra. Recall that the image measure induced by this measurable function is denoted by f sub star mu. And if I have a set, say E, on the codomain, if I want to take the image measure of this set, what we do is we take the inverse image So this inverse image now lives in the domain X. And if this is now a subset of X, it is meaningful to take the measure of this set. Well, the measurability of F guarantees that this is in sigma, provided that here E is a measurable subset of Y. In other words, E is in tau. Okay, so this is a way of assigning or constructing a measure from or a measure of the codomain Y out from the measure mu of the domain X and a measurable function F that maps X into Y. So the question that we would like to address is the following. How can we calculate the integral of some function g, some non-negative function or an integrable function with respect to the image measure f star mu? So this integral can be computed as follows. So let's start with the assumptions. So I have a triple x sigma mu, which is a measure space, a pair yt, which is a measurable space, and a function f from x to y that is measurable. And let us consider a function g defined on y to k bar. So again, k bar is either the extended real numbers or the complex numbers. And suppose that this is measurable. Now, then g is a non-negative measurable function on y, okay, respectively an integrable function on y with respect to the image measure if and only if the composition GOF is measurable now in X with respect to the sigma algebra sigma respectively integrable with respect to the measure mu. And in this case, okay, the integral over y of g with respect to the image measure is the same as the integral over x of the composition g of f with respect to the measure mu. So this is the integral over the image measure. So we integrate with respect to the measure mu, but we just applied to the composition of G and F. Okay, so now here non-negativity and measurability of G and the composition are equivalent can be proved easily, since we know that the composition of two measurable functions is again measurable. With regards to integrability, it is enough to prove this equation, since if one is finite, then the other term is also finite. So let us look at the proof. Let's start with an A in T, that is the sigma algebra on Y. And suppose we consider a special case where G is the characteristic function. So we have the following chain of equivalences. So the characteristic function of the inverse image of A under F evaluated at some point X. This is 1 if and only if, of course, X must be in the inverse image. And we know that this is equivalent to, by the definition of the inverse image, f of x in A. And in terms of a characteristic function, this is equivalent to the characteristic function of A evaluated at f of x equals 1. But take note that this one here is the same as the composition of the characteristic function and with f evaluated at x. So from this, we see that okay, the characteristic function of the inverse image is the same as the composition of the characteristic function of A with f. And therefore, okay, we want to prove this in the case where G is the characteristic function. So replacing G by the characteristic function. And take note that we are integrating here a simple function. Hence, this is the same as the image measure of A. And according to the definition of the image measure, this is mu of f inverse of A. However, this is nothing but the integral over x of the characteristic function f inverse A with respect to the measure mu. And applying this equation here, this is the same as the integral of the composition of the characteristic function and f. So therefore, we have verified this equation in the case where G is the characteristic function. Now, since we know that the integrals are equal or coincide in the case of characteristic functions, as what I have explained in the last lecture with regards to the Fubini-Tonelli theorem, from this we now apply the Lebesgue-Dubois-Reymond strategy to conclude that the above equality of integrals also valid for non-negative measurable functions and hence for integrable functions. So to recall that, once you have once you know that the integrals are equal in the case of characteristic functions, you then apply this to simple functions by linearity. Since a simple function is nothing but a finite linear combination of characteristic functions. In the case of non-negative measurable functions, you approximate your non-negative measurable function by an increasing sequence of simple functions, and then apply the monotone convergence theorem. And then for real integrable functions, you separate the positive and negative parts and apply the result for non-negative measurable functions. And finally, in the complex case, you split it according to the real and imaginary parts, and then apply the real case. So this is basically what I called the Lebesgue-Dubois-Reymond strategy. So this theorem here allows us to establish the following change of variables formula, namely for let's say for affine transformations. So let's start with a Borel set U in Rn, an n by n matrix M, and that and it is also invertible, and a vector A in Rn. So think of M as the scaling matrix and A as the translation vector. So if, let's say, I have a function g, which is either a non-negative measurable function in U with respect to the restriction measure or restriction sigma algebra, Borel sigma algebra, so BU, or it is integrable in Rn with respect to the, or in, I should say U, and it is integrable with respect to the Lebesgue-Borel measure lambda n. Then the integral over U of G of mx plus a dx is the same as the following. So 1 over the absolute value of the determinant of m. So we are guaranteed that this is non-zero because m is invertible, over the integral of mu plus a gy dy. Recall that here dx is what? A shorthand for d lambda n x, and dy is a shorthand for d lambda n y. So if in the case of the Lebesgue-Borel measure, we do not emphasize the measure lambda to the n in this case. So symbolically, this means that we use the change of variables from x to y as follows. So y here is equal to mx plus a, and therefore if x, so x is in u, if and only if y is in mu plus a. And quote unquote, if you put this on this side, you have something like, working on differentials loosely, dy is, so I should say dx is equal to 1 over the determinant of m dy, loosely speaking. So here, this is how the change of variables work in multi-dimensions. So let us look at the proof of this formula. So I want to apply the previous theorem, and it is clear what is f in this case. So let us define f from u to mu plus a as follows. So f of x is equal to mx plus a. Then we know from our previous discussion that this image measure is the same as 1 over the determinant of m, absolute value, times the Lebesgue measure. So if the function f is this affine function, then the image measure with respect to the Lebesgue-Borel measure is just a scaled version of it, namely the Lebesgue-Borel measure multiplied by the reciprocal of the absolute value of the scaling determinant of the scaling matrix. Okay, so according to this, let us start with the left hand side, and we wish to show that this is the same as the right hand side. Okay, so emphasizing the Lebesgue-Borel measure and taking note that f is mx plus a, we have this d lambda n x. And we know that this is, okay, since f maps from u to mu plus a, so we have mu plus a. And according to this previous theorem, we're going backwards. We have the integral over this set of g. Now we use the variable y of the image measure, lambda n y. According to this equation, we have the following. D of 1 over the determinant of m d, or I should say lambda n y. And you can show that this is the same as 1 over the absolute value of the determinant. So again, you can prove this via the Lebesgue-Dubois-Reymond strategy, wherein you can factor out the constant, the non-negative constant, in the case of for this measure. Again, you can immediately see this in the case of characteristic functions, and hence for any non-negative or integrable function. And here, let us remove the notation for the Lebesgue measure or Lebesgue-Borel measure. You have this identity, which is basically the one stated here. So as special cases, let's say if I take in star with M the identity matrix, we obtain the following formula. So M now is the identity, so we have x plus a dx. So this is now the integral over mu plus a g of y dy. And this is the translation invariance of the Lebesgue integral. So translating your function and integrating over the translated domain does not change the value of the Lebesgue integral. So this is reasonable. For instance, you have, let's say, your domain U. Just think of an interval at this point, and you want to, let's say, integrate over this domain. And for this, let us just imagine or use the Lebesgue-Riemann integral and visualize this as an area. So translating, let's say, with the vector A. So this is now U plus A, assuming that here A is positive, and I should correct this to U plus A, okay? Since M is the identity matrix in this case. So if we move this, we should get the same integral. So that's translation invariance. Another special case is by taking in the star where M is, let's say, some scalar alpha, where alpha is not equal to 0, and the translation vector to be 0. So in this case, the integral of u g alpha x dx is now equal to 1 over alpha to the n so we should have an absolute value here. Alpha u g of y dy. This is the case since the determinant of M so the determinant of alpha times the identity matrix is alpha to the n. And of course, we should take the absolute value. And we call this the scaling formula. So if you scale your argument, you will have this scaling factor 1 over the absolute value of alpha to the n. So roughly speaking, if you think of y equal to alpha to the x, then dy is, let's say, absolute, well, let us concentrate on alpha being positive. So dy would be alpha to the n dx. Here we have a power n because we are now in the dimension. We now have n dimensions. Okay, so therefore you can think of dx as 1 over alpha to the n dy. And roughly this is this formula. But we need to be very careful in the case where alpha is negative. We need to take the absolute value. So as an example, let us consider the ellipse in R2. So denoted by E. So I have here two parameters A and B, and this ellipse is the set of ordered pairs y1 and y2 in R2, such that y1 squared over a squared plus y2 squared over b squared is less than 1. So this region, so let's say this is the y1 axis and y2 axis, then this should have a coordinate A, and this should have a coordinate B, or y2 component B. So we know that we can transform the circle into an ellipse. And for the sake of simplicity, suppose that we take the unit, a ball. Okay. So here, let's say this is x sub 2 and x sub 1, and I want to map this unit ball into the ellipse E. So let us denote the interior of this to be the unit ball. Okay, so F maps the unit ball onto the ellipse, and this is defined as follows. So what we do is we stretch, at least in this figure, stretch in this direction and stretch also in this direction by factors A and B respectively. And you can immediately see that indeed this maps the unit ball to the interior or to this ellipse E. And of course, this is the same as, okay. Or we now take our matrix A to be AB 0, 0. Since you can write this as A times x1, x2. And if you want to be precise, you need to put A transpose in this case. And this should be M. Okay, and the determinant of M is AB. And since A and B are positive, so you have this. So we can now calculate the two-dimensional Lebesgue measure of the ellipse. And this is nothing but the area. So this is the Lebesgue integral over E dy. Here, if you want to be more precise, you need to put d lambda to y. And according to the transformation formula, we have the integral over the unit ball times the absolute value of the determinant of M, the x. Again, if you want to be precise, you can put d lambda to x. So this is a constant. In fact, this is equal to AB. Hence, we have AB times the two-dimensional Lebesgue measure of the unit ball. But we know that the area of the unit ball is pi, so this is a pi AB. Okay. So the area of the ellipse is pi times the product of these parameters A and B. So this the area here is pi, and the area here is pi AB. So without any trigonometric, let's say, transformation, we computed easily the area of an ellipse. And this reduces to the area of the circle if A and B are equal. And of course, the common value would be the radius of that circle. So in the succeeding lecture, we will generalize this to where's that? So we will generalize this formula star in the case of non-linear transformations.